So this is our introduction to transformations in pre-calculus and honors pre-calculus. First, we're going to break down the various pieces that are parts of transformation. The first is a translation or a shift. And if we want that shift to be down or up, what we're doing is taking the function value and we're adding or subtracting a k. If we want it to shift down, are we adding or subtracting a k value? Good, minus k. If we want it to go up, we're adding k. It's outside of the function, so it affects the y value. If instead we want it to move left and right, that's impacting the x value. As a result, it's going to be in with the x. But what's odd about this is when you're in with the x, it's the opposite of what you expect. If we want it to move left, I normally think about that as a minus. But what do I put inside here? Plus h. Whereas when I want to go right, it's going to be the opposite of what I expect. I'm going to see a minus in there. And that tells me move right. When I want to reflect across the x-axis, which values are being multiplied? The y values or the x values, which are being multiplied by a negative number? The y values are, right? Whatever used to be up here is being reflected over the x-axis, which means they've turned negative. So we're putting a negative distributed across the whole function. It's impacting the entire y value. Whereas if we want to move it from here over to here, all we're changing is the x value. So the negative is on the inside. When it comes to compressions and stretches, the word always messes with me here. Which one is a compression, the wide one or the narrow one? Nope. Because this is the vertical one. If it's stretched upward, these walls come in and get pulled upward. So pack it over on the stool over there. So the stretch would be if I take a times f of x, and a is a value that has a bigger number than 1. And by putting absolute value, we're taking it the reflection component. If I want it to compress, in other words, push this whole thing down to be flatter and wider, I'm still going to multiply something by f of x, but what kind of number would this a be? Yeah, it's going to be between 0 and 1 as an absolute value. By taking out the absolute value, we're removing the reflections, right, which are up here. And the function will compress or stretch vertically, in other words, the y values, by multiplying by a, whatever it is. So this is a compression, and that's a stretch. For horizontal dilations, again, this happens with the x. It's inside with the x. So although there's a b being multiplied by this, what's going to happen is you're actually going to divide by it. It's going to be the opposite. You'll multiply by 1 over b. And so if I take my x values, and this was supposed to be an x value of 1, and say I've got 2 in here, when I multiply by 1/2, my x value is no longer 1. It's now in there. It's 1/2. So horizontal compression gets narrower, whereas a horizontal stretch gets wider, which just messes with my brain. So this is where b is a big number. And if b is that fractional value like we had over here, then what you end up with is dividing by a fraction less than 1 is like multiplying it. And it ends up moving farther along the x-axis. Any questions on the basics of transformations? This is a reference sheet that should allow you to reference this when doing work. But of course, I need you to be able to recognize not just transformations on parabolas, but on all the functions. So we need to know the parent functions. What's this parent function called a linear function? y equals x. What's this parent function called an absolute value function? What's the parent function of a quadratic? Y equals x squared. What's the parent function of a cubic? X to the third, or cubed. Flip to the next page. We'll come back and do more of those in a second. What's the parent function for a square root? Y equals square root of x. What about the cube root? Cube root of x. It doesn't look so great, but that's supposed to be a little 3 up above the square root symbol. What about the reciprocal function? Good. What about the exponential function?
Yeah.
We could look at it as e to the x, the natural exponential function, or we didn't have a's or b's in any of the rest of these, but it sure could be y equals a times b to the x also. This makes more sense to me because it covers more ground, but a times b to the x. All right, now those functions are covered in regular pre-calculus, but you guys are honors. So you're also doing logarithmic functions. What's that look like? What's the parent function? And we learned about this one last class. Do you remember this one? We got a value of like negative 0.9, and we said that rounds to be negative 1. Yep. Can somebody explain to me what this graph is showing us? Let me let everyone look at it for a second. Okay, what's it showing us? If you had to explain this graph to somebody, how would you explain it? Harris?
You have to round down. So
you have to round down. So if I put an x value in of 1.5, when you round 1.5 down, I get a y value of 1. And whether I'm at 1, 1.1, 1.2, 1.3, 1.999, 1.9999, I'm still at 1 until I hit 2. When I hit 2, it's not at 1. Now it moves up to 2. And it stays there, 2.1, 2.2, 2.3, 2.4, 2.5, 2.999. And when I hit 3, it bumps up to 3. Now, you guys did a little bit of sine and cosine in geometry. And then last year, you guys did unit circles, didn't you? Okay. So notice the scaling here. What are these marks here? By pi. So do you think these are in degrees or radians? Radians. So you assume this is in radians. That's fine. What's our function going to be? Y equals sine of x. Now, let's see about this. And what about this one? Let's just get that one in. Yeah. Let's start with an easy one of these parent functions to begin with. Let's do like reciprocal. Would you please take a moment, work with your neighbors, and fill in all this data about the reciprocal function? We'll go over it in just a second. let's take a look. Can someone please raise their hand and give me the domain of a reciprocal function, parent function? Yes, Jason.
Um, if negative infinity is zero, and then the union with zero to infinity.
So you're choosing interval notation. I love it. Negative infinity to zero. And then there's nothing at zero. We don't get to use that value. And then it continues on to infinity. Great. Someone else with a range? Exactly the same thing. Coming from the bottom up, it comes up from negative infinity to zero, not including that value. Then it jumps and starts on zero, not including going up to infinity. X-intercept. Somebody new, please. Thank you, but raise your hand so I know who it is because I don't want everyone, I don't want it being owned. What about y-intercept? Yes.
None.
Again, please raise your hand and I'll call on you rather than just shouting it out. Any extreme on this one? Is there a maximum or a minimum? No. It looks like it's approaching zero, but it never quite hits zero. So we can't say zero is the minimum. So, and in fact, it goes down to negative infinity over here. So we can't use infinity or negative infinity as extrema because they're not numbers. So we'd say none. They're concepts. Increasing interval. Do we have any increasing parts of this function? As we read left to right, it keeps dropping lower, and then it starts up here, but then it drops lower. So there's no increasing interval. Decreasing interval. I'm coming from the far left here, so negative infinity, up until zero. Not including. Pop quiz, do I ever have a hard bracket during an increasing or decreasing interval?
No.
Nope, because at an individual moment, it just doesn't increase or decrease. Yes. Because I'm still going. Because I start at zero and it decreases to infinity.
But doesn't it like have like a little gap between at zero?
It does. So if I wanted to include zero, I'd have to like have one of these sides have a hard bracket. I don't. They're both open brackets. What the union suggests is I'm taking the solution over here, so all of this stuff minus this little line at zero, and then I also want to include all of this stuff. So it's everything except that little gap at zero. The union tells me I'm using the left side and the right side both. End behavior. This is new for you. This is going to become really important when we get to calculus. This is a way that we describe things like horizontal asymptotes. What we want to say is over here, as we work towards the left, what do you think the y value is getting really, really, really close to, but never hitting? So we'd say as x approaches negative infinity, f of x approaches zero. And how would we express it for the right-hand side? We're still doing x. As x approaches infinity, f of x approaches zero. Are there any discontinuities in this shape? Yeah, there's.
But with the end behavior, it's only with the x.
It's what?
It's only with the x, not with the y.
It is. Because we talk about where we are on the graph with the x values. The y values refer to kind of what values we're achieving at that point. But x is our navigation. Are there any discontinuities? If this is electricity and you ran electricity from the left here, would it continue? It pops here, doesn't it? So at x equals zero, and then this is what's called an infinite discontinuity as opposed to a jump like we used before. Last one, even or odd? Odd, good.
How do you know?
How do you know if it's even or odd? Does it reflect over the y-axis? Does it reflect over the x-axis or 180-degree rotation?
Reflects about the origin.
Reflects about the origin. Yep. Okay, please move forward 2 pages.
And then you grab it.
If you flip 2 pages forward, you're going to get to identifying transformations. And let's just jump way down to this one. Nah, let's do number 9. First question. What's the parent function? Good. Absolute value of x. Understanding that that is our parent function, we can see that we have several transformations. Somebody raise your hand and give me one when I call on you. Yes, thank you, Will.
Vertical stretch by 2.
Good. This one out front is outside of the y value. So that's a vertical stretch. Scale factor of 2. How about this negative? What is this negative to? Let me get some new blood in here. Is it inside the function with the x, or is it outside the function? If the parent function is absolute value, isn't it inside? It's inside the function.
It's a reflection on the y.
It's a reflection of the x values, which is over the y-axis. What about this -3 in here? It's a translation, right? It's in with the x, so is it moving right 3 or left 3? Right 3. Translation. Right 3. So for this page of identifying transformations, you're simply listing the parent function and then all the transformations you can identify. Now, does this look similar to what you just did? Does this look similar to what I just did? I would like to suggest something different here. Let's put the parent function in. That's fine. What's the parent function? Instead of listing the transformations here, put them over here outside this box. So we're going to have a vertical reflection over x-axis. We're going to have translations. This is 1 right, and this is 7 up. See if you can read my chicken scratch. Sorry about that. But here's how you graph this. I can think of 2 ways that I would graph this. The first way is I would recognize what's the parent function here. It's a V. I know that graph. I know that it has an origin of 0, 0. Girls in the front, I need you to stop talking, please. That includes laughing. You need to go outside and calm yourselves down. Go take care of that, please. Absolute value of x starts at 0, 0, goes over 1, up 1, over 1, up 1. It's got a slope of 1 going this way, a slope of -1 going this way. And then we're going to have this translation. The vertex is going to be 1 unit to the right and 7 units up. And this reflection is a vertical reflection. So instead of going over 1, up 1, like we did a minute ago, it's going to go over 1, down 1, over 2, down 2, over 3, down 3. And so it ends up being something like that. Looks like my slope is a little off because these slopes should be parallel. But that's a sketch of it. I don't think that's the way you guys did it, though, right? In advanced algebra, when you did transformations, I would guess you did this. You said, I'm going to create a list of values for the parent function. Here's my x, here's my y. I know enough about the parent function to know that it should be in the domain between -2 and +2. And when I then plug those in for x, I see what my values are. And then I can say, all right, so that's my parent function, but for this f of x, what's happening to the x values? What transformations are we doing to the x values? It's just this thing in with the x, -1. But we know that what happens inside the x is the opposite of what you expect. So I'm going to take my x value and add 1 to it. Regarding my y value, my function is being multiplied by a negative. It's having a negative or a reflection. And then we're adding 7. So what I'm going to do now is I'm going to take this x value and apply this rule. -2 plus 1 makes -1. -1 plus 1 makes 0. 0 plus 1 makes 1. 1 plus 1 makes 2. 2 plus 1 makes 3. And the corresponding y values to the parent function are going to undertake a different transformation. -2 plus 7 makes 5. -1 plus 7 makes 6. 0 plus 7 makes 7. 1 plus, -1 plus 7 makes 6. -2 plus, hold on. Yeah, that's right. -2 plus 7 makes 5. And now I can plot those. We can actually use the same graph here. When I have a new x value of -1, my y value is 5. So that's why my graph was off, because it's supposed to be up here. 0 is supposed to have a y-intercept of 6. At 1, it's going to be up here at 7. At 1, it's at a max. At 2, it's at 6. At 3, it's at 5. And so I end up with a graph like that, which looks a little bit better. Does this sound more familiar? Is this the way you guys did it in advanced algebra? No? How did you guys do transformations? Interesting. Okay. Let me ask this. 5, I have facility in performing transformations by either one of these ways. I could graph this. 5, yes. 3, I used to be able to. I think I can get there again. 1, I never was before. I never will. Bah humbug. Okay, good. Hands down. I would recommend that you consider going to these parent functions that you're going to be putting in place and coming up with what some critical values are, right? Like for the square root function, you might say, you know what I really use for this is I'm going to start at 0, 1, 2, 3, 4. And then I'd find the square roots of those. Maybe I don't even care about 2 and 3 and just give myself my critical values. With that, you can then apply them for the functions.
Yeah.
Do you have to do those critical values?
Yeah.
No, but what I've just given you is this graphic organizer of all your parent functions. I think this packet is one that you'll keep for a while. It's got all your transformations on it. It's got all your parent functions on it. I think this is going to be an important tool for you. All right, last thing I want to point out. Is let's take a look at the sign. If I talk about domain of sign, actually, let me do this. Would you guys please work with your partners and try to fill this chart piece in for sine curve. I'll come back and go through in a second. So I heard people talking about the things I want you to talk about. Was domain pretty reasonable? Yeah. If we're using interval notation, it's simply going to be, open negative infinity to positive infinity. And the range is what?
Hard bracket.
Hard bracket -1, hard bracket +1. I'm sorry? For range, no. Range is going from -1 here, this says -2, up to a +1 here, this says +2. Now, here's where it gets weird. What are the x-intercepts? It's pi, it's 2 pi, it's 0, it's -pi, it's -2 pi. How could I? And it goes on forever. 5 pi? It goes by pi, right? Every pi, starting at 0. And somehow what we have to convey is that it's every pi that are integers. 1 pi, 2 pi, 3 pi, 4, 5 pi, 6 pi, 7 pi more. So what we're going to say here is we're going to say x such that x equals 0 plus or minus pi k. And k is accepted as an integer. We know that it means 1 or 2 or 3. It doesn't have a decimal to it. So 0 plus or minus an integer value of k. It could be 1k, 2k, 3k, 4k. What about the y-intercept? 0, 0. That one's easy. What about the extrema? None? A lot of them. So what we've got is maximas. These are absolute maximas, right? We have values of pi over 2. And then there's another one over here, which is 2.5 pi or 5 pi over 2. And then this one is going to be 1, 2, 3, 4. So that's going to be -3 pi over 2. Somehow we have to figure out a way to create an equation, kind of like we did here, for all of these values. Easiest way I think to do that would be to say, this is like an anchor point, and then I go 2 pi to the right and 2 pi more, 2 pi more, because 2 pi is like 360. That's a full cycle. And so I can either add or subtract 2 pi from pi over 2. So I'd say x equals pi over 2 plus or minus 2 pi k. What about the absolute mins? This one's 3 pi over 2. This one's negative pi over 2.
Same thing, but -pi over 2.
Beautiful. Find your anchor point and say x equals negative pi over 2 plus or minus 2 pi k. Could you have also done that with 3 pi over 2 instead of negative pi over 2? Yep, that would have been fine too. Okay, I think I've given you enough of an idea with those and let you play with that. So this packet is going to prepare you for the next stuff that comes. Please be thoughtful about it. It is a lot of work, but it will be a useful tool. So write neatly, make your work visible, talk to your neighbors, and come through with this stuff.